Hello everyone, and welcome to my presentation on electromagnetic scattering from Ford circles. My name is Christian Rose. I'm a junior at Southern Illinois University Carbondale. I'm a double major in mechanical engineering and physics, and my mentors for this project were Dr. Sharjesh and Dr. Kochik. Can you hear the shape of a drum was a question popularized by Mark Kac in 1966. It was well known at the time that if the geometric properties of a planar membrane are known, then it's possible to calculate the normal modes of the membrane using the corresponding wave equation. If one imagines the membrane to be a drum, the normal modes would represent the pure tones which the drum could produce. The question was then proposed, if the information of all normal modes is known, is it possible to identify the shape of the membrane? At the time of Kac's paper, it had already been proven by Menashe and Durham and Plagel that the perimeter or circumference of the membrane could be calculated, and Herman Weyls' formula had also provided a method to calculate the membrane's area. Later on, Michael Berry would extend Weyls' formula to the case of a fractal membrane. It's in the same spirit which we approach scattering from fractal configurations. Scattering studies have led to advancements in many fields, including material identification, nuclear engineering, and obtaining properties of a given system. Fractals are defined as being self-similar to an infinitesimal scale, meaning that they are patterns which repeat forever. Fractals are abundantly found in nature and are used in modeling, image compression, and engineering design. The fractal that we will specifically be observing is known as Ford circles. We have chosen this fractal because the position of each circle is well defined using a process known as Ferry addition. Although the circumference of Ford circles diverges to infinity, the area is finite and even well known. Here's an arrangement of Ford circles where we've set r equal to 1. If we notice first the larger two circles on the outside, we see that they are tangent to each other as well as to a horizontal axis. If we insert a circle in between these two, which is tangent to both as well as the horizontal axis, and we repeat this insertion process to infinity, we will obtain a configuration of Ford circles. The position of each Ford circle can be obtained using Ferry addition, which is the addition of two fractions where the numerator and denominator are added separately. If we begin with the first two circles, we have 0 plus 1 over 1 plus 1, which gives 1 over 2, which is the central position of the center circle. If we repeat this process for the center circle and the circle on the left, we have 1 plus 0 over 1 plus 2, which gives 1 over 3, which is the center position of the circle, which is tangent to both previously neighboring circles as well as the horizontal axis. We also notice that the position of each circle is given as an irreducible fraction. And if we write this fraction as some p over q, where p and q are coprime integers, we can extract information on the radius of the circle, which is equal to the vertical position of each circle. This is given as 1 over 2q squared. And we can verify this by observing the larger two circles, which have a denominator equal to 1. This means that q is equal to 1, and 1 over 2 times 1 squared is 1/2, and we can see that the radius of each of the larger circles is 1/2. We note that if r was equal to anything else, that these coordinate positions would be scaled by the factor of r. We begin by closely following the scattering formalism produced by Schwinger's group, which begins at the fundamental equations of electricity and magnetism, known as Maxwell's equations. We invoke the radiation boundary condition first introduced by Sommerfeld in 1912, which allows us to break the electric field into its incident and scattered components. We can then set the incident electric field to be of a monochromatic plane wave form and focus on solving for the scattered wave. This leads to a scattering amplitude expression, small f, which is dependent on the angles theta and phi, as well as the frequency omega. We see that we have a 4 pi in the denominator, c represents the speed of light, and we see that the scattering amplitude is proportional to the electric susceptibility of the material, which is here dependent on a difference of wave vectors k minus k prime. If we replace this difference by a new wave vector, which we simply call k, we see that we can obtain this expression by taking the Fourier transform of the electric susceptibility dependent on a position vector r. The electric susceptibility in position space is given as 4 pi times lambda, which is the atomic polarizability of the material, and we introduce a Dirac delta function, r minus r prime, which constrains us to the boundary of the scatterer. We begin with scattering from a single circle. If we observe the diagram, we notice that the vector rho naught denotes the position of the center of the circle, given at an angle alpha above the x-axis. Rho prime is involved in the Dirac delta function, and it traces the outer edge of the scattering circle. The vector s has a magnitude of the radius of the circle and can be rotated about the circle by manipulation of the alpha prime angle. K and K prime both have the same magnitude of omega over c, where K is chosen to be in the direction of the incident wave, which is also the z direction, and K prime is in the direction of the scattered wave. We choose K prime to also be the location of the observer, which is located at an angle theta away from the z-axis. After carefully crafting a Dirac delta function to express the position of this circle and evaluating the resulting integrals, we obtain this expression for the electric susceptibility, where lambda is the atomic polarizability, A is the radius of the scatterer, K perp is the planar component of K prime, and J0 represents a Bessel function of the first kind. If we recall our scattering amplitude equation, we note that we had to divide by 4 pi, and we see that there will be a 2 pi a that pops up in this expression. Therefore, we know that the electric susceptibility is proportional to the circumference or perimeter of the scatterer. So when we move this expression to the case of Ford circles, we expect a divergent quantity. If we replace the radius a by 1 over 2q squared and sum from q equals 1 to infinity to represent Ford circles, and we also have a new summation from p equals 1 to q, where the greatest common denominator of p and q equals 1, and we see in this exponential that the horizontal and vertical position of the Ford circles define the exponential itself. We can then closely evaluate this expression and notice that in the case of forward scattering, when theta equals 0 and k is in the same direction as k prime, that the expression can be simplified greatly. The Bessel function of 0 reduces to 1, and the exponential term with an exponent of 0 also reduces to 1. The sum from p equals 1 to q, where p and q are coprime of 1, is defined as Eulers' Totient function, which counts the number of integers less than and coprime to a given number q. This function is typically represented by the Greek letter phi. We also see a Riemann zeta function where q equals 1 to infinity of 1 over q squared is a Riemann zeta function of 2. There's also an identity relating the Eulers Totient function to a Riemann zeta function, where it is equal to the zeta function of the argument minus 1 over the zeta function of the original argument. Here we've obtained a full closed form expression for the forward scattering amplitude of Ford circles. We also notice that the zeta of 1 is a divergent quantity, which aligns with our suspicion that the scattering amplitude would diverge. Here we've obtained a closed form expression for the forward scattering from Ford circles. We would now like to invoke the optical theorem, which relates the imaginary part of the forward scattering amplitude to the total scattering cross-section. Once we obtain this, we would like to plot the scattering cross-section for all angles theta and phi. We would then like to extend our derivation to Ford disks, where the circles are replaced with disks, and the circumference should be replaced by the area of the disks. We expect that this will result in a finite expression for the Ford circles. I'd like to give a special thanks to Dr. Sharjesh and Dr. Kochek for their mentorship. This research has been funded by the SIUC McNair Scholars Program, and my email is listed below if you need to contact me. I would be happy to entertain any questions at this point. Thank you.